So this is the last video in the block number 1 where we are going to use parametric approach based on, in this case, in normal distribution to describe our experimental data. And I'm going to use people XLSX dataset like I did in one of the previous exercise videos. So I'm going to load the data. I'll just use the code from this B13l from the first learning sequence. And if I run this code, you will see that I forgot to make it a working directory. So if I run it again, you can see that I get the data set. And if I open the data set, you can see it's the same data. We have 13 columns. 12 of them are different characteristics of 32 persons. You can see height in centimeters, weight in kilograms, and so on and so forth. We have several categorical variables like hair length. It's coded -1 for short hairs and +1 for long hairs. We have sex, which is coded biological sex, which is coded -1 and +1, -1 for males, +1 for females. And then we have also region, which is also coded with these two dummy values, -1 and +1, -1 for Scandinavia and +1 for Mediterranean region. Okay. So I'm going to analyze height of people in this case. So first of all, I need to understand how many populations we have. So we have 32 persons, we have 32 height values. Can we treat all 32 values as coming from the same population, or we have different populations, meaning groups which have different distribution of the height values? In order to analyze this, I will start with a non-parametric plot with a box plot where I plot height values, first of all, versus combination of sex and region, because I believe that these are the two categorical variables that can influence the height. Data equal to D. Yeah. Okay, so this is it. So you can see -1, it means males from Scandinavia. +1, -1, it means females from Scandinavia. And then we have males from Mediterranean region and females from Mediterranean region. What can we see? We can see a very clear difference between males and females. But there is not very clear difference between, for example, between regions. So if we take, for example, females from Mediterranean region, from Scandinavian region and Mediterranean region, there is no clear difference. You can see that we probably can treat height values as coming from two different populations, meaning height of males and height of females. Okay. So let me do this. First of all, I will split the data set to males and females first. So I will just use a function subset for that. I say take dataset D and make a subset where sex is equal to 1, and that will be my females. You can see DF, meaning dataset for females. If I open it, you can see I have 16 values only, and by looking at the name of the people, you can clearly identify that they are female names. And then I can do the same for males, DM, and then sex equal to -1, and then you can see the same. We have DM, also 16 values, and if I open this data set, you can clearly see these are male names, right? So now we are ready, and since we are going to use the parametric approach, we assume that these values came from normally distributed population. I need to compute the parameters, so I need to estimate parameters because I don't have the population parameters. Normal distribution has two parameters, average and standard deviation. So let me compute the average and standard deviation first. I will not use DF and DM to compute it. I will use the global dataset D because I have a very nice function aggregate that will do it for me. So I just say M equal to aggregate, and then D. No, I need to write a formula, right? So it will be height values depending on biological sex, data equal to D, and then I need to say function equal to mean. In this case, you can see I will get two mean values. Actually, it's not mean values. You can see it's a table with two observations and two variables. The first shows the sex levels, -1 for males and +1 for females. And this is the average height in each group. You can see that males indeed have much higher, not much, but I mean 17 centimeters larger average height comparing to females. And then I can also compute the same way. I can compute the standard deviation. And in this case, I just substitute mean with SD. And then you can see this is the standard deviation. So you can see standard deviation is more or less the same. Here we have 4 centimeters, and here we have 4.3 centimeters. Okay. Since it's a table with 2 columns and I need only the values, right? So I can just take only the second one, the second column here, and only the second column here. So this construction looks a little bit weird, but actually, if you think that aggregate instead of this code, it returns this table with 2 rows and 2 columns, and then for this table I say take a second column of this table, then it makes sense. And then if you look at M, you can see that it's indeed just a vector with 2 values. And same here, aggregate returns table with 2 rows, 2 columns, and then I say take only the second column, and then you can see now I have S. Okay. So now I have the parameters, estimated parameters. I don't have the real parameters of normal distribution. I have only estimated parameters, and these estimates, they are based on the sample statistics. Okay. So let me start with distributions, right? So I'll make a distribution histogram for height of females. So for height of females. So you can see that it looks like a very nice bell-shaped histogram in this case. Also, we have only 16 values. The histogram looks pretty good. And what I can do, I can make it first of all density distribution by say frequency equal to false. You can see by default it's frequencies, so it's counts. If I say frequency equal to false, it will be densities. Don't worry about this, it's a warning. But now I can also add a theoretical curve and see how well the histogram matches the theoretical curve. I simply compute it. I know that the smallest height is 155, the largest height is 175. So I simply say generate height values, let's say from 150. So I go a little bit wider to 180. And then, for example, the length of this generated vector is 100. So I generate a lot of height values. And now I can compute the densities, right? So I can say the density is density for normal distribution for XX values. And then I need to use this average and standard deviation. You remember in average, the first value is for male and the second value is for female. So I need to use a second value here. So second average and the second standard deviation. So that will compute a lot of, not a lot, but 100 exactly density values. And now I can use these values, these computed values, to add density distribution, probability density function, theoretical probability density function on top of my histogram. I use function lines, xx, ff. We did the same for uniform distribution in one of the previous videos with our exercises. I say it's, let me say it's color equal to red. And then I will make it kind of a thick line, 2, line width equal to 2. Then if I run it, you can see the lines is on top of the histogram plot. You can see that my limits are not good enough, so I need to adjust the limits here. First of all, I will make x limits a little bit wider. I will use the same 150, 180 range. And then y limits also need to be a little bit wider. For example, you can see this one is 0.06. So probably if I use 0.1 from 0 to 0.1, it should be okay. And then you can see indeed it's okay. Well, it's not a perfect match, but you remember that histograms can look weird if you have not enough data, because histogram is based on accumulated values, right? So you need to accumulate enough frequencies to make a good histogram. But even in this case, where we have only 16 values, so you can see a pretty good match between the histogram and the probability density function, theoretical probability density function based on these estimates, right? What else I can do? I can also make the percentile plot and CDF function, right? So to make the percentage plot, I need to know the sample size. So my sample size is just the number of rows. I can just write 16, of course, but let me use number of rows in DF. So you can see it's 16, right? And now I can compute first of all, I need to order the values. So I can say X, let's take height values from this height of females, and then let's sort them. So they are sorted as non-decreasing sequence. So first it's the smallest and largest the largest. And then I compute the percentages by using these rings from 1 to n minus 0.5 divided to n, right? So that's the way we compute the percentages, the sample quantiles. And now I can make a plot, X and P, and then I will use, for example, both, and then that's it, right? So this is my percentages versus the real values. And now I can also make this CDF plot, right? So I can say the CDF function is P norm for XX. I just reuse this XX values, this the height values, generated theoretical height values. Then I use the second average and the second standard deviation. And then I can add a line, XXFF, again, color equal to red, and the thickness of line is 2. So you can see this is the line. Actually, I can change the plot. I can use type B, which is just a scatter plot. And then if I can make it, you can see that indeed the theoretical line fits the points very, very well. So I can even compute some measures of fit like R squared and so on and so forth. I'm not going to do that, but you can see a very good fit here, right? Now what I want to do, I will combine this together. So I say par MF row equal to C22. So it means I expect 4 plots, not 2 plots, but you will see later which 4 plots I mean. And then if I run all this code again, you can see that indeed, so this is the female's height distribution histogram and the theoretical probability density curve based on the estimates. And this is again, we have the percentages, the sample quantiles, and then the theoretical CDF function, cumulative distribution function, and then you can see a good match, right? What is missing, I would like to add a main title to this plot. I will just write that these are females, right, like this. Okay. So if I run it now, you can see it here. Now what I'm going to do, you probably understand, I will just copy and paste this. And I will also add a height of males. So instead of DF, you can see this is the previous code. This is the previous code. And then I can use DM here. I change females to males. And then I know that the limits will be different. So I know that males in this case are taller. So I will use from 200, let's say, let me just look at the smallest and the largest value, right? So let me just look at the range of the male height. So this is the range. You can see the smallest value is 175, the largest value is 198. So let me use between 170 and 190. And 190. I will keep the limits here the same. And now when I generate this XX values, I will use the same limits from 170 to, not 190 of course, because 190 is smaller than this one. Let me use 210. So it should be larger than 210. And now I need to use the first values in my M and S vectors. You remember that in M we have 2 average values, males and females. Male average is the first value, so that's why I use first value here. And then the same for standard deviation. So this is standard deviation for males. It's the first value in this vector, and that's why I need to use first value here. And then the same here, I just need to change DF to DM. And then also here I use first average. And here I also use first average. I think that's it. Now let me save it. Let's use B13A. So it means it's a third learning sequence in block number 1. And then A means it's the first part. So now we have also males. And then you can see for males, your distribution is kind of skewed. We will investigate it in a minute. But for females, you can see the distribution looks pretty good. Okay. Now the next is to investigate why is this skewness really a dangerous thing? So can we use normal distribution for describing males values? Because if you look at this kind of plot, it looks more or less okay, right? So the fit is not that bad. So it means that we need additional investigation in this case. But for the sake of simplicity, let's investigate both values for the normality. We know what to do. We know that we can compute skewness, we can make a QQ plot, and then we can also make a normality test or check for normality. Okay, now let's try. So first of all, let's start with QQ norm plot for females. So DF height. And then I would like to get back to my original split where I have only one plot. So I will just say MF row equal to C11. So this is the QQ plot for females. You can see we indeed have a very, very good linear trend. But in order to see this trend a little bit better, I will use cuckoo line function, which adds a theoretical line. And then you can see that the cuckoo norm plot shows that indeed very likely these points, these measurements or observations, they came from normally distributed population, meaning if I have not 16 females, but 16,000, 16 million females from these regions, then the distribution will be perfectly normal, right? I can, for example, make some colors if you want, like this. Then you can see that it's just a normal plotting function scenario. You can change anything you want. Okay. Now let's do the same for males. Again, I'll copy and paste this. And then cuckoo norm and cuckoo line. And then I change F to M. And then let's check this plot for males, right? And for males, you can see that most of the points, they look very nicely, except this one. So we have some extreme point here. So what to do with this extreme? Because height of 198, it's not kind of outlier, right? So we can have persons whose height even taller, who are even taller. So it means that we cannot just remove this point just because we don't like it, right? So let's investigate how likely we can get a sample as extreme as this one, or maybe even more extreme, although the population is normally distributed. So maybe it's just a sampling problem. So in this case, we need to use a normality test, Shapiro-Wilk test. So I will do again the same. I will run this test for female persons, for height of female persons first, and then for males. So I say Shapiro test, df height, so this is the females, and then you remember that I'll just run this again. This is how cuckoo norm plot looks for females, and it looks pretty good. So we expect that the p-value for Shapiro test in this case will be pretty high. And indeed it's so you can see it's 0.97. So it's very likely. So 97% of the other samples taken from the same population will look as good as this one or worse. And apparently most of the samples will be worse because this one looks almost perfect, right? Now let's do the same for males. So I use dm here. And then you can see that the p-value is pretty low. So in this case, I mean, it tells us that this extreme value here, it makes our sample looks not very nicely fitted by the normal distribution, right? Why we have this? But probably it's because the sampling is wrong. So maybe we need a little bit bigger sample size and so on and so forth. But at least if you, for example, use a 5% threshold, so we cannot continue we cannot treat these values as coming from normal distribution. But still 1.3% of the samples or 1.4% of the samples will look even worse, similarly or even worse if it's indeed normal distribution. So in this case, we're kind of on the border, on the edge. So we can try at least to use normality description here. Okay. And what means using normality description? Actually, you already used normality description because you already show I'll show you this again. So you can see I combine these two, statistics, average and standard deviation, and that's exactly what parametric description in this case is, right? So you show the center of the distribution and you show the standard deviation. However, you can visualize this data. In this case, if we assume that we allow it to use normal distribution, you can visualize this data graphically, and that will be a new plot to learn. Well, the idea is following. First of all, we make a bar plot for average values. So this is the bar plot for average values. So this is average of males and this is average of females. Let me add these names. So just write names equal to C, males and females. And then females. Okay. So you can see that this is the average values. And now what I'm going to do, first of all, I will save what bar plot returns, and I'll tell you what it returns. It returns, you can see two numbers, 0.6 and 1.9. It's a position of this bar along x-axis. You can see we don't have x-axis because we have categories. We don't have any values along x. But the position of these bars, the middle points of these bars, is defined by this p. For example, if I make AB plot, AB line, vertical, that's wrong, vertical line P, you can see that these two vertical lines, one located at 0.7, one is located at 1.9, they exactly crosses the middle point, right? So I'm going to use this knowledge to do the following. Look, there is a function in R that adds arrows two plots. For example, I can say arrows, and then I can say average, and let me use like this, P and average, and then P and M minus average. Let's see what it shows us. I provided four vectors, right? So first of all, it's X position of the bars, then the average, so it will be just these points, right? And then again, X position of the bars, and then the average minus one standard deviation. And this average minus one standard deviation, this is exactly what I want to show in the plot. So I would like to show not just average values, but also variation, how big the variation is of the values. And I use just one standard deviation for that. So let me show you what it adds. So it adds an arrow to the bottom, right? So you can see this is minus one standard deviation, and this is minus one standard deviation. I can do the same for plus one standard deviation, right? So I can just write plus S. And then you can see that, first of all, it looks very weird. Here we don't have enough place for that. And here we kind of have enough place, but you can see because it's arrow, so it looks very strange. So what we can do? First of all, we can add a little bit of place. For example, we can say while limits is between 0 and let's say 210. So let's see if it helps us. Yes, it does. And now what I can do, I can change angle of these arrows to 90 degrees. So I can say angle equal to 90. And then also do the same here, angle equal to 90. And then if I run it together, now you can see this, what is called error bars. So you have mean as a bar, and then you have variation plus minus one standard deviation around mean as error bars. So this is a very common plot if you want to show, for example, characteristics of different groups in form of center and variation. And usually when you use parametric approach, variation is plus minus one standard deviation. We know we can go beyond that, but that's variation for 68% of the values. And that's a very common way to show to compare the groups. Okay. Of course, it's just a plot. You can also change, for example, color. You can change color, let's say pink. I know border equal to NA. Let me show you what it means. You can see that we have pink color inside and border color. NA means not available. So it means no border color. I can, of course, make it, for example, red. Let me just show you. Red. And then the border will have red color. You can see it here. Let me get back to NA. And then, for example, I can use red color here. So color equal to red here. Color equal to red here, right? And that will give me a plot like this. This is obsolete. And this should be plus. I made. So now it looks good. Yeah. What else? You can also add a little point here. So that's also very common in these plots. You can just write points. Again, X position of the middle point of the every bar, and then average. Let me use point character 16. It's a fillet circle, and then the same color red. So that will give you even a better plot like this. Okay. So this is another way to represent your data graphically, where you have several groups and you want to kind of show what's going on inside each group and how these groups relate to each other. This is very common to show average value from each group as a bar and standard plus minus one standard deviation interval as an error bar. It's called error bar plot. Okay. So that's actually it. So the overall idea to use parametric approach is that, first of all, you need to test your values. If they indeed came from normally distributed population, you use cuckoo norm for visual testing, and then you can use Shapiro test for running normality test to get a p-value, which tells you how extreme your sample is for this null hypothesis for default assumption that indeed population is normally distributed. And if you pass the Shapiro test, for example, you use threshold of 5% or 1%, it's up to you, then you can use the parametric description, you can compute standard deviation, you can compute average, and then report your values in form of standard deviation and in form of average and standard deviation, and visualize it using this error bar plot. What else? In the lecture, I also mentioned skewness, and you remember that if I go back and make I can actually use this arrow left to show you the previous plots. I hope it will not be too far away from here. Yeah, this one. So remember that in this case, we have a kind of a skewed distribution because of this outlier. So we can check it by computing skewness. However, R doesn't have the built-in function for computing skewness, so you either need to write your own, or you can install a special package which has this function. And I know there is a package, it's called Moments, and this package has additional functions for statistics, including function for computing skewness. So let's install the package first. I go to Packages, click Install, and then I write Moments. So you can see Moments. And then I just click Install. You can see something is going on here. Now, no error messages, so probably I have it installed. You can also see it here. If you scroll down, you can see that indeed we have a package Moments, install it. It's Moments, cumulants, skewness, kurtosis, and related tests. Yeah. Now I load this package by using library Moments, run it. And now all functions from this package are available for me. So for example, I can say skewness, and then df $height. So height of people for data frame where I have values only for females. Then you can see the skewness is minus 0.03. You remember, ideally symmetric data have skewness equal to 0. And this is very close to 0. So it's pretty good value. Now I can also compute it for male persons. Skewness for male persons. And then you can see it has a right skew, right? So it's a positive, so it means it's a right skew. And you can see it's pretty large number. It's pretty far from 0. So that's one of the reasons why actually normality test shows such a small p-value, because skewness is pretty large. Okay. So that's another way to test your data for normality. It's actually not for normality, it's more for symmetry, but it's a nice complement for the QQ-plot and for the normality test. Okay. And then finally, what you can also do, you can make this sample. You can take a random sample from normally distributed population. That's what we use the rnorm function for. For example, if you know that average, let's use again height of values, right? Let's say we want to take a sample of size 10 from a population whose average height is 165 centimeters, and for example, standard deviation is 5 centimeters, right? So if I run it, you can see I get exactly 10 values randomly taken from this population. You can even make for example, let me do the following. I can show you this, and then make a histogram, hist_x, right? So in this case, I know that it's perfectly normally distributed, but the sample doesn't look like a bell-shaped distributed, because you remember the sample size is small, so therefore the histogram is quite misleading. So you don't have enough values actually to make a good histogram. But if I increase sample size, and then you can see it looks better and better, still not symmetric. So if I compute skewness for my values, you can see the skewness is not 0, it's 0.4, not large, but still some positive skewness. Also, we know that this data came from normally distributed population. I just did it using the computer simulation. I know it's almost perfect sample, and it's pretty large sample, but still you can see it's not perfect, right? In this case, you can see a small negative skewness. Now it's almost perfect. It's the skewness at least is 0, and so on and so forth. So you can see every time I take a new sample, the histogram looks pretty different, right? Sometimes it looks nicely, like a bell-shaped curve, like this one, and sometimes it looks a little bit weird. Of course, if I take a sample of 1 million, then it will look almost perfectly bell-shaped. So that comes us to final conclusion, right? So when we talk about normal distribution, the normal distribution describes really large set of values. So you need to have like million of values in order to use normal distribution precisely. But when we take a sample, we call it a sample that was taken randomly from normal distributed population. You still can use normal distribution to describe the sample and to make different inference about your sample, what we are going to do in the next block. So it's still possible. So you can still use this parametric approach. Just remember that your sample if your sample size is small, it doesn't represent the whole population very well. Okay. So now that's it for block number 1. Now you know how to describe your data, your experimental data, using 2 different approaches: non-parametric approach based on ranks, parametric approach based on theoretical distributions. You learned 2 theoretical distributions. It's uniform distribution and normal distribution. And now you're ready for the next block.